In this video, I will explain about dynamic braking. The motors pull a short circuit with the controller's power stage. Braking current starts to run in a closed circuit and the motor brakes quickly.
This figure is meant to demonstrate the basics of the dynamic braking. First, we are going to look at how current normally flow through a circuit. Power supply feed currents to the driver unit. The driver unit then directs the current into the motor according to its settings. The current then passes through the motor continuous to flow the circuit. Now, we start the braking. Notice the two switches inside of the driver unit. This direct the flow of current, and now by changing them, flow will also change. Switch 1 cut off the feed from the power supply, and switch 2 change position to close. This change creates a closed circuit between the motor and the driver unit. As a result of this, the motor works as a generator that supplies the nail from enclosed circuit. With braking circuit, this generates the braking force needed to slow down the motor.
Hello. Hi everyone. So today we are going to do some experiment on the dynamic braking system. First of all, we are from Group 5 and my name is Ahmad Nur Aiman bin Muhammad Ajar, metric ID MH17009. So today I'm going to explain the experimental apparatus that we use on this experiment. So this is our power supply, which will connect to the switch and the traction motor, and this power supply will supply the voltage around 12 volt to the traction motor. We use traction motor, a DC 12 volt motor which produce a rotation, and this cylindric square aluminium will provide some inertia to the rotation of traction motor, which will create some difference between the what's going on between the when we with dynamic braking system and without dynamic braking system. So my friend Farhan Hakim will continue to explain the experimental procedure, and my other friend Muhammad Nur Hisham will explain on the regenerative braking system afterwards.
Okay, my name is Muhammad Farhan Hakim bin Muhammad Rashdan. My ID number is MH17028. Okay, our experimental procedure is, as you can see, this is the power supply, which is 12 volt, and this is the traction motor, which is 12 volt also. So as you can see, power supply is connected to the main switch, and after that is follow through the dynamic braking system. So as you can see here, when I switch on the main switch,
the traction motor will start rotate, and when I turn off the power supply and turn on the dynamic braking switch, the traction motor will directly stop.
okay, so this is the digital multimeter, which is for recorded the voltage when the dynamic braking system is applied, and this is the stopwatch to measure the time interval between when the main switch and the dynamic braking system is applied, and for the wheel to stop. Okay, that's all for me. Thank you.
Okay, this is time required for a normal system for braking. Okay. Okay, this is time required for dynamic braking. You can see the difference between the normal and the dynamic braking. Thank you. Hi, my name is Muhammad Nursham and I will do the experiment for regenerative braking. Okay, the first one is we take a LED and then we will attach to the powers to the system. Okay. Okay, this is LED. You can see this system just like a turbine. Okay, when we rotate this, it will generate the power and then indicate the LED. The same function as turbine, and this will be supplied to the back to the power supply, and then we gain current from braking. Thank you. Okay, this is how the regenerative braking works. Okay, you can see this multimeter. You can see the increment of the value when I rotate the wheels. Okay, first we will cut off the power supply, and then I will rotate this. You can see this. Okay, you can see the increment in this multimeter. This is how the regenerative braking works in the real life. Okay, hi. This is our calculation for the braking system. We use the dynamic braking system. Okay, this is the scenario, which is we have 184,612 the weight of the train. Okay, for the calculation for the traction force, this is the formula, which is PV 33,300 minus 525 V, which is the maximum, the speed. Okay, the speed we choose in this scenario, which is the maximum speed, 70 miles per hour, that we convert to meter per second, we have 31.29. Okay, and then we calculate, we have traction force, this one. Okay, for the drag formula, we have QV equal to 2000 plus 20V plus 3.5 V squared. V is the speed. Okay, then we substitute the value of the velocity, and then we get 6052.52 Newton. Okay, for brake force formula, we have B equal to mass times gravity times beta, which is beta provided for all train, which is 0.09. Okay, we substitute the value of mass, the value of gravity, which is 9.81, and then the value for beta, and then we get this value 60,299. 993.9 Newton. Okay, we calculate the deceleration when the train is about to stop. Okay, the formula is MF equal to PV minus QV minus B minus MG sin alpha. Okay, the sin alpha is for the situation the train go to the incline rail, which is we don't have, we just a straight line, so we can remove it. Now we have PV minus QV minus B. Okay, we have all the value for PV, QV and B, and then we substitute, and then we can get
negative 152.173. Okay, then we will divide it by m value, which is mass, and then we get negative 0.8243 meter per second squared, which is this is the deceleration for the train when we apply this brake. Okay, for the time taken for train to stop, we have TV equal to integration of 1 over AU squared plus BU plus C, which is the value for A is Q2 over M, for B Q1 over M, and C we have Q0 over M plus G bracket B plus beta plus gamma. Okay, we will substitute all this formula. Okay, this is the value for Q. This we can refer to drag force formula, which is this is the Q1, Q2 and then Q3. We can substitute back into this formula. Okay, when we integrate V to 0, we can get 31.29 over 18.173 plus 0.1061 and plus 0.1185, and then we can get 1 minute 0.7007. Okay, this is the time for the train to stop when we apply the dynamic braking. Okay, for the distance travel, we have the same formula, but we will integrate U, not 1. For the time we use 1, but for the time travel we use U, which is SV equal to, this is V, sorry, 0. Okay, U over A, which is we use the same value at which is we use the same values, same as time taken formula. Okay, we can get 31.29 squared over 18.173 plus 0.1061 plus 0.1186, and then we can get this value 532.216 meter, which is this is the distance for the train stop when we apply the maximum speed. Thank you.
Okay, we are from
Group 5.
Thank you for watching.
Don't forget to subscribe.
Like
and share.